Hey everyone, welcome to This Explainer. Today, we're going on a seriously fascinating journey. We are going to track a single ray of sunlight all the way from its tiny microscopic interactions on a rooftop panel right through to its massive global footprint. If you've ever wondered how these sleek slabs of glass and silicon are actually reshaping the world's energy landscape, you are definitely in the right place. Because think about it, how exactly does a random sunbeam, traveling millions of miles, turn into the electricity that powers your lights, your fridge, and your phone? Well, to answer that, we're going to have to bridge the gap between microscopic quantum physics and massive macro grid power. It's this elegant, honestly almost magical process of taking photons from the sun and literally forcing them to move electrons in a wire.
So, here's our roadmap for today. First, we'll hit the physics of solar power, then mono versus polycrystalline panels. Third, we'll look at weather, nighttime, and storage. And finally, the true environmental impact.
All right, let's dive right into Section 1, the physics of solar power. To really get how solar works, we have to zoom way in to look at the atomic structure of single crystal silicon. Silicon is atomic number 14, which means it has 4 valence electrons in its outermost shell. Now, in a pure crystal, every single silicon atom perfectly shares its 4 valence electrons with 4 neighboring atoms. It creates this absolutely perfectly symmetrical, incredibly stable diamond lattice, where all those electrons are locked tight into covalent bonds. But here's the catch. In this perfect frozen state, pure silicon actually doesn't conduct electricity very well at all. Why? Because there are just no free electrons to move around and carry a charge.
So, you might be wondering, how on earth do we get a current to flow? Well, enter a process called doping. Doping is this brilliant trick scientists use to free up those locked-in electrons so an electrical current can actually happen. Basically, by intentionally introducing specific impurity atoms into that perfect silicon lattice, we can completely change how the material behaves.
Let's break down how this works. Think of it like donating and accepting. If we introduce a phosphorus atom, which has 5 valence electrons, 4 of them bond perfectly with the silicon. But that 5th electron, it's kind of left hanging. It gets easily liberated by thermal energy, and boom, it becomes a free electron that can cruise around. We call this an N-type semiconductor. On the flip side, we can use a boron atom, which only has 3 valence electrons. It readily accepts an electron from a neighboring bond, which creates an empty space, literally a hole for a charge to move into. We call that P-type. So when a sunbeam, a photon, hits this carefully engineered setup, it knocks electrons out of place. And because of this specific doped structure, those electrons are forced to flow in one single direction. And there you have it, an electrical current. Okay, moving on to Section 2, mono versus polycrystalline panels. Let's look at how all this atomic physics gets packaged into the hardware we actually put on our roofs. When you're shopping for solar, you're mostly going to run into 2 main options, monocrystalline and polycrystalline. The big difference here all comes down to manufacturing. Monocrystalline panels use a pretty complex process to grow a single, extremely pure silicon crystal into an ingot, which is then sliced up. This ultra-pure structure creates less resistance for those electrons we just talked about, so they can flow super freely. Plus, it gives the panels this really sleek, uniform black look. Polycrystalline panels, on the other hand, are made by melting multiple silicon crystals together and just pouring them into a mold. That creates a bit more resistance for the electrons, and it's what gives those panels that familiar, sort of marbled, bluish hue. Now, what's amazing here is seeing how that pure monocrystalline silicon translates directly into real-world performance. That single crystal structure gives monopanels a higher efficiency. We're talking sometimes over 23%, and a massively long lifespan of up to 40 years. But as you might guess, that complex manufacturing process means they definitely come at a premium price. Polypanels are a little less efficient, but they offer a much more budget-friendly entry point, which is great if you have plenty of roof space.
But check this out. Here's a totally surprising fact about these high-tech panels. They actually lose efficiency as they get hotter. No way, right? The typical temperature coefficient for a monocrystalline panel is negative 0.3 to 0.5%. That basically means for every single degree Celsius the panel heats up above its optimal testing conditions, it loses up to 0.5% of its efficiency. So a blazing, scorching hot summer day isn't actually when your panels are operating at their absolute peak efficiency. Kind of wild, right?
All right, zooming out to the household level, let's hit Section 3, weather, nighttime, and storage. First things first, we've got to bust a major myth right now. the idea that solar panels are totally useless in bad weather. While direct sunlight is obviously the best, panels still capture what's called diffuse irradiance. That's just light scattered by the atmosphere. In fact, one study looked at panel efficiency during an actual hurricane, and guess what? The panels still outputted 18 to 60% of their normal clear sky capacity, even under that insanely heavy cloud cover. So yes, they absolutely still pull their weight on a gloomy day.
So the crucial takeaway here is that while panels can handle the rain, they for sure do not produce power in the dark. Without photons, the whole physics process we just covered literally stops. But there are some pretty robust solutions to make sure your house stays powered up after sunset. You can store your excess daytime energy in lithium-ion batteries. You can use net metering, which basically lets you export your daytime extra to the grid in exchange for credits to use at night. Or you can go with a hybrid system that smartly switches between the two. To really ground this battery storage idea, let's look at a concrete real-world example. A standard 10 kilowatt-hour lithium-ion solar battery can power a typical house, say one using 5 kilowatts, for about 2 solid hours. This perfectly covers that super crucial evening window right after the sun goes down. You know, when everyone's cooking dinner and blasting the AC or turning on the lights, dramatically reducing your reliance on the grid when electricity is usually the most expensive.
Okay, let's zoom out for the final time. Section 4, the true environmental impact.
When researchers impartially look at the big picture, the life cycle assessment, they break the solar life cycle into 4 main stages. You've got year 0, which is raw material mining, digging up stuff like silver and copper, and the super energy-intensive production of the silicon itself. Then comes installation and grid connection. After that is the long operation phase. And finally, years 25 through 30 involve decommissioning and disposal. The data here is clear. The absolute highest environmental footprint happens right out of the gate, during those production and construction stages, heavily driven by the massive amounts of electricity and aluminum needed to just build the panels in the first place. So we're looking at a very real yes-but situation. Yes, manufacturing takes about 660 grams of silicon per panel, involves some toxic mining, and generates roughly 50 grams of CO2 for every single kilowatt-hour of energy that panel will eventually produce. However, when we impartially compare that to fossil fuels, it's kind of mind-blowing. Traditional coal generation pumps out a massive 1,000 grams of CO2 per kilowatt-hour. The emissions from solar manufacturing are practically a drop in the bucket compared to the ongoing, non-stop emissions from coal. Which brings us to a super vital metric, the energy payback time. Because solar panels churn out perfectly clean energy once they're actually on your roof, it only takes about 1 to 4 years for a panel to completely neutralize the carbon debt it created during manufacturing. After that short little payback window, every single watt generated is entirely carbon negative relative to the grid. It's paid its dues, so to speak. And the long-term payoff? Absolutely incredible. A standard 10 kilowatt residential solar setup reduces carbon emissions by roughly 4 tons every single year it operates. To put that into perspective, that is the environmental equivalent of planting over 100 trees year after year. When you remember that these panels stick around for 30 to 40 years, the net positive impact is honestly just staggering. Which leaves us with this final thought. We've seen how tweaking silicon at the subatomic level creates an electron flow that can reliably power our everyday lives. And we've seen how the life cycle of these panels overwhelmingly benefits the planet, even with those upfront manufacturing costs. So, as efficiency technology keeps improving and panel recycling gets better and better, could the tiny atomic reactions happening right above our heads eventually pay off our entire planetary carbon debt? It is a truly fascinating future to think about. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.